Hello everyone, this is Alireza. Today I will speak about a theory behind what we will work on in next episodes, and that is our node editors. Node editors look very complex in first glance. Some of the examples that people know is Shader Forge, and I think it was Playmaker. Then we have, of course, Behave from Angry Ants, and it's version 2 also. Then maybe Behavior Designer. Then we have what? Strumpy Shader. That is old asset and it's not updating anymore, but it's open source. Then Node Canvas. And what else? Something inside Unity that people doesn't pay attention. Mechanim is again a node editor. And PLY Gain has two node editors as much as I investigated. One for Dialog and one for, no, actually it's for only Dialog because Dialog is both a dialog editor and a quest manager. Now, if you look into this list, you will see that it looks like node editors are behaving differently. For example, these two first behave totally different than these two. And Strumpy Shader was like Shader Forge. Node Canvas is totally a different asset that handles different types of node editors by itself. Mechanim also behaves differently, and these two behave differently, okay? But in reality, all of them are the same. For example, you have this graph. It has a bunch of nodes. And these nodes connect to each other, obviously. And sometimes, I don't know, a node can connect to different two nodes. Now, each graph will start from somewhere, okay? Each graph will, not always it's the same. We will take a look at another example later. But most of the nodes, at least, have a start node. The very first frame that graph is getting updated, it will evaluate this start node, and it will tell the graph which nodes to evaluate the next frame. Okay, so this node is responsible to set the active node on the next frame. Based on its logic, it will set this node, for example, to be the active node. So next frame, this will be evaluated. And it has no children, so it should put another node in the graph as the next active node. And most of the time, when it's no children, two things happen. One, it jumps out of the node, out of the graph. It says, okay, this graph is finished. Or it will set the parent back to be active, and this time it will go for another children, or maybe the same children, depending on the logic. And this guy can jump back or set a children to be next active node. So this is the type that mechanism behaves, and behavior trees behave. They can set their children or their parent as active node, but at the same time they will send a success or failure message to their parent. Okay? So Shader Forge. Shader Forge is a very special graph. In Shader Forge, your start node is a node at the left side that is your shader. It will connect to a bunch of nodes that can connect to different nodes. For example, something like this. And there is, although this is a start node, don't forget that, there is no way that Shader Forge would go for only single node, because it's compiling a shader at the end. Okay, so how will it behave? Well, it will evaluate all the nodes at the same time and put them into a final shader, the result, and compile that shader. This needs a binary search, plus reverse problem solving. It's the most complicated node tree that I had seen by now, and I'm not making this. It's a very complicated algorithm. But let's see what will be in each graph. So first, each graph has a starting node, has a start node. 2. Two types of graph exists, and I'm totally ruling out Shader Forge type. Okay, the first type evaluates all nodes each frame. We will take a look at this example, for example. B, only one node per frame will be evaluated. Okay. 3. Logic for node evaluation exists in node itself. Okay. And a rule about this second type of nodes, that only one node is evaluating itself. In type B, the node, the node is responsible on selecting next active node. So the graph has nothing to do with it. 5. Beside evaluation logic, each node is responsible of drawing its GUI. What does this mean? Well, if you think about it, a graph is only, so let's say this is a graph. A graph is only a scriptable object. Nothing more than that. This scriptable object will consist a list of nodes. Okay? And each node is again another scriptable object and has its own members and handles its own members. For example, it can have a float, it can have a string, blah, 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 blah. Okay? And every member here should be used inside the node. If a node needs to send something to another node, then, for example, a float value, only one thing per connection can be transferred. For example, a node can have more than one output. One of them is float, for example, one of them is a string, one of them is the value of the logic inside the node, and I don't know, whatever. Here is a vector, for example, vector 2, okay? And this is the value. So if we have some nodes that has one or two, or for example, 3 inputs, if I hook this connection to here, it will only send the float from this connection. It won't send the value. If I want to send 2 things to a node, for example, the float and the value, obviously, first of all, I need 2 outputs and I need 2 inputs. So per connection, we will send only one member. At the same time, because the node is a scriptable object, don't forget that, scriptable objects. First of all, because of the rules of a scriptable object, one, we can't create them in runtime at game runtime. Okay. Second rule is that it can be serialized by Unity. So we don't need to write, sit down, pull our hair, and write our own serializer, deserializers. 3. It can be read in runtime. Don't forget that. That's a very critical part. And as I said, each node should evaluate itself and each node can send or receive one param or parameter per connection. Now, if we remember these, then we will compare different node graphs to each other, and we will say that we'll see that they work the same. For example, a behavior tree. Okay, this is a behavior tree. Each node can be connected to different nodes, and that's the start node on top. Okay, so most of the time the start node is a sequencer. Sequencer node tells that, hey, evaluate your first child. Okay, so next frame this guy will become active node, and if it returns a success, then evaluate the next child, so it will become the next active node. It returns success, then evaluate the last node or the next child, whatever. Okay, that's sequence. But when the first frame it sets the first child as active node, it will look if it has children and what is its logic. For example, let's say that this is another sequencer. So it says, okay, I'm another sequencer node, so I will evaluate my first child. So next frame, this guy will become active node. So if we go for orders in frame rate, this is the first frame, this is the second frame, this is the third frame. It will evaluate itself and return a success or failure. Let's say it returns a success. Then the next frame, so because it's sending success, at the same time it will set this guy as active node. So frame 4 it will become active node, and frame 5 it will set its next child as active node. Okay, it evaluates itself. It says, okay, I was successful, so it returns success. So frame 6 this guy will become again active node. It says, okay, both my children are successful, so now I return success to you. So frame 7, this will become active node. Okay. Then he says, okay, first child was success, go to the second child now. So it will become frame 8. Frame 8, let's say it's another type of node. I forgot the name. Sequencer, and well, there is a node there. I always forget that node's name. It evaluates only childs, and one success would be enough. So it evaluates his first child. It's 9. It's a sequencer, for example. Then it evaluates this child at frame 10. This child, let's say, returns failure. At the same time, it sets this guy to 11. Okay, so these two won't be evaluated next because it's a sequencer. It will return failure. It will become frame 12, and this guy is active node. So it says, okay, I had a failure. I can't send success now because I need at least one success. So it will evaluate this guy at frame 13. It returns success. So frame 14, this guy will become active. It returns success. This is frame 15. So it will become active node again. And it says, okay, I have 2 success. Now it's the last node, so frame 16. And it's again one of those 2 that will return only 1 success. So it will evaluate this guy at frame 17. It returns success this time. And it's frame 18. It's evaluating itself. It says, okay, I got 1 success. So immediately I set this guy to frame 19. active node, and I return success at the same time. And frame 19, when this guy is evaluating itself, it says, okay, all my nodes are success, so my job is done. I have nothing more to do. I will return success, but this time, because I'm a start node, the success means graph ends. So 19 frames for this node. And remember, if it was a success here, we would evaluate for at least 4 more frames, 1 for each frame and 1 for the parent. Okay? This is the type of behavior tree that it's working. Second type of node graph. It has no start node. We have a bunch of nodes that connect to each other one way or another. And this, for example, connects to here, another node connects to this, then these two connects to another node. So because we have no start node, we have no special order here. Each frame all nodes evaluate themselves. Okay, for example, let's say this is a float node, this is a plus node, add node. So we have 2 floats, and this is another float node, this is a multiplier, this is an integer node, and this is a minus, and this is again, let's say, multiplier. Okay, so at each frame a loop will happen. At the loop, this node will send in his value to this guy. This node will send in his value to this guy. And in reality, it's not happening. It will only evaluate itself and says, okay, float value equals to this. This will say float value equals to this. Now, this node will reversely look to its children, get their value, and evaluate itself. Then one of these nodes evaluates itself, another node evaluates itself. Then this guy wants to evaluate itself, for example, because it's totally random. It will look into the child. It doesn't need any value evaluation. Okay, it returns the value. It gets it. Then it looks into this child, and this child should send something. But at this point, it may have 0 because it's not evaluated. So it will return 0. But at the same time, again, this one gets evaluated. For example, next frame, next loop, I mean. Then at next loop, it will evaluate and get some number. But this node has that I minus 0 for time being because it's not evaluating again. Okay. So it will send in, for example, this is the last node that gets evaluated, okay? So this guy will get I minus 0 plus the result of 2 floats on top, being plus to each other, okay? So we lost one node here for first frame. Okay, is it acceptable? No. Because the result can hiccup, you know, for one frame. It can jitter. We don't want that. So in reality, when you are developing some nodes graph like that, people by nature tend to add the nodes the way they use them. So they add a float node, for example. Then they add another float node. Then they add the plus node. Then they connect these two. Then they add another float node. Then they add a plus node and connect it and say, oh, okay, I need another branch. So float, plus, and connect. This is bad because this guy will evaluate itself before this guy. So the way to handle these, and I said these guys are really complicated, is that you choose a node in the list. Okay, let's draw that graph again. So these guys has connection, these guys has connection, these guys has connection, and finally these two go into the final connection. Now, we will still use the loop, sorry, okay? So we select the first node. We check if it is evaluated. If it's evaluated, then continue the loop. You don't need to do anything. If it's not evaluated, then evaluate. Evaluate. And set that flag to true. Then continue the loop. Okay? Then we go for the next node. Okay, it's not evaluated. Evaluate it. Okay. Then go to the next node. It's not evaluated. Evaluate it. When we want to evaluate it and then we are getting the children, we will check if they are evaluated or not. If they are not evaluated, first evaluate them, then get the value. Okay? And then the next children, of course, we check if they are evaluated or not, then get the value back. The next frame, for example, it will be check, okay, it's not evaluated, evaluate itself. Next frame, we will evaluate this guy. Now, it looks to this guy, it says, okay, this is evaluated. This guy, however, is not evaluated. So first, evaluate himself. Now, that will look, okay, my children, this is not evaluated, evaluate, get back the value, evaluate, get back the value. Now I'm evaluated, send back the value. And at the last, and for example, next frame, we will next iteration to the loop, we want to evaluate this guy, but it's evaluated, so break. This guy will be evaluated. It's evaluated already, so continue. We have nothing to do. This guy is evaluated. Continue. We have nothing to do. Then we come to this guy. It will check the first child. Okay, it's evaluated. Get the value. It's evaluated. Get the value, and we get the final value. This is the true way of doing it. So we are first checking children, checking if the child is evaluated. If yes, get value. If no, first evaluate, set the flag. Set the flag will happen inside the child itself. So, sorry. First evaluate, then get value. Okay? And at the end, set the flag for yourself. Now, what happens after the end of the loop? At this time, all nodes has evaluated flag. Should we keep this flag? It depends on the behavior you want on these node graphs. Some nodes graphs need only evaluate once. For example, Shader Forge need to evaluate their nodes once and then compile the shader. Okay, so when it's evaluated, it's okay. We have the values unless something is changed, unless the user is changing something. Sometimes, so the type A needs a evaluation only one time. The second type of the framework may need evaluate each time frame lapse. For example, each frame, or for example, I don't know, every 3 seconds. It's up to you. But in this type, when the loop is ended, the graph will send in the result. So graph sends the result to its caller, then reset flags. And wait for the next iteration. So, for example, let's say that we have a script that is mono. It has a timer. Every 3 seconds, it will evaluate the graph. So it sends the signal to the graph to run yourself. The graph will evaluate its nodes, okay? Then it has every node evaluated, and this script is responsible of getting the result of the graph back, okay? And again, reset all of them to be not evaluated. The script will wait for 3 seconds. After 3 seconds, it will send it to evaluate yourself again. So first at run, it sent evaluate, gets the result back, then sends reset command, and then after the timer, it sets evaluate, okay? These type of node graphs are used lesser than others, but if you take a look at behavior trees, for example, a behavior tree node is a combination of both of them, meaning that one node at each frame will be evaluated, okay? And at the end, this type node or each one of these children can jump out of the graph for the result. Sometimes this result is a command. For example, move to a vector tree. Okay, but sometimes when the top node is evaluated completely, the result is only a success or a failure. So if it's sending a command, of course, it's sending a success too. So success plus a command. In these times, a script outside has a time intervals, and in each interval, it will evaluate it. Then, for example, 3 seconds later, it will evaluate it. 3 seconds later, it's evaluated again and again and again. So it's infinite loop. Every 3 seconds, it will load the tree and send the evaluate command to a tree. So another example is a dialog box. Dialog box has a start node and maybe more than one end node. The start node, for example, goes into a dialog, then that dialog goes into a condition node, or from this condition it may end, or it may go to a quest giving node. This quest giving node, depending on its results, may go to different dialogues. Again, this dialog, and this is a dialog, can go into a condition. The first condition may end here, the second condition may end here. These two dialogues, for example, can go into the same end. Okay? Something like that. Or even, to make it more interesting, where's my mouse? Or even, one of these nodes can go back to here. Okay. So at the frame 1, the start node will evaluate, and of course it will set this node to the second node. Okay. So this is frame 1. This will be frame 2. Frame 3 goes here, evaluates itself. Now the result can be this as frame 4 or this as frame 4. Let's continue because it's end. I will not go there. Let's say that this is the frame 4. Now frame 4 can set one of these to frame 5. Let's say that it was this. Then frame 6 can go here, and these two may become 7. Now if this guy becomes frame 5, this will become 6. If this one will become 5, this will become 6. And this time, for example, this will be 7, this will be 8. Or again, this will be 8, and it continues on and on. And if you not be careful about your conditions, you can end up in an let me choose another color for this. You can end up in this loop. And it will become infinite loop. So you should be careful about how you are handling this node and this node. These two are responsible. One of them will be responsible for an infinite loop. So you should be careful about this condition. But long story short, here a script will sit outside, and at the start it will evaluate the start node. Okay, but then at update or at any trigger, I should say, each time it's triggered, it will tell the node, the graph itself, to evaluate active node. So here we don't have intervals, but we have a trigger. And each time the graph is evaluating, it will evaluate only a single node, not all the graph. So you can immediately say it's cheaper. Tons cheaper than something like a whole graph or a behavior tree. Because maybe a behavior tree needs to go to the end result of a branch until it evaluates outside. Or maybe this last one is jumping out. So it can be cheap if the very first node, for example, is a command plus result. So it will jump out the node. Or it can be very heavy if the graph is complex and the last node is the node that will respond to everything. These type of nodes may be cheap if we have few nodes, or may become heavy if we have tons of nodes, let's say. But when I'm speaking about heavy nodes, I'm speaking about something between 3 to 10 milliseconds. Nothing more than that. If your graph, the whole graph, will evaluate himself above 10 milliseconds, then you should revisit your code and rewrite everything there, because that's not proper. This type is always less than 1 millisecond. Because it's only going to the graph, it will evaluate, and most of the time a dialog editor is responsible to set a text on GUI. Nothing more than that. In this particular example, it may evaluate 2 nodes. So it comes to the quest node, it says, okay, hey, the quest was not given, now the quest is given. So evaluate yourself this time, and the next iteration, it will evaluate only this node and says, okay, the quest is not complete yet. So this is the result. This is the next condition, actually. Okay, so the quest is not completed yet. So go back here and show this dialog. If it's completed, then hit the end node, and end node will jump out of the graph. At the same time, it will show it GUI text. For example, I have nothing to do with you. Whatever. Okay? So dialog systems are very cheap. Don't forget that. Quest systems. And I'm completely speaking only about the graph itself, not the backbone needed for the quests. So a quest will be given, okay, and it's a start node. The start node will see if I should give the quest, then it gives the quest. Now this quest most of the time goes into a condition node, and this condition node decides if we have no quests, so end, or if I should give another quest. Okay? And this quest again can go into a condition node, it will end, or it can go to a new quest. It goes into a condition node, it can go to another end node, or it can jump totally to the first quest, or any quest in the graph, for example, a new quest or a loop. So here again is the danger of having an infinite loop. Maybe you want it, maybe you don't want it. So you should be careful. In this condition, quest graphs are cheap again, because at each frame or at each evaluation, only one node will be evaluated. And this node will immediately, for example, in condition node, activate the next node, or in quest node, it will activate the next node that is condition. It won't iterate through all of them in one frame. No, it won't do that. So at each frame, only one node will be evaluated. If it's the end node, it will jump out of the graph. There is nothing to do. Okay? And at the same time, you may want to, have a node, a special node that is a reset node, and it will set the start node as your next active node. So your graphs, long story short, after all this babbling, graphs can have start node, if they have the start node, or may not have the start node actually, can evaluate more than one node, or can evaluate only one node. If they don't have the start, so no start nodes, no start, then we use a loop for sure, and we evaluate all nodes. There's no way around it. So a graph again can have end nodes or may not have end nodes. Okay? And that's the bottom line. In next episode, we will start implementing a graph. Before that, I should speak about the design of two graphs, the two possible designs. One of them is vertical design. In these type of graphs, a node will start from top, will connect to the nodes at the bottom, and the graph continues on vertical. If you need to, for example, evaluate nodes in sequence, for example, in behavior tree, the order is first from top to bottom, then from left to right. That's a standard. A graph design that is horizontal will have its start node at the left side, and it will connect to the children at the right side. Okay? So the order is left to right first, and if it's in sequence, then top to bottom at second. Personally, I like the vertical graphs for two reasons. One, let's speak about horizontals and their shortcomings. Your nodes in design most of the time are more horizontal than vertical. It's very rare that you see some nodes like this. So if you want more than one output, either you will just draw a button and use that to draw the lines, or if you want to draw different slots, you are limited on the number of slots. Also, because it's more designed horizontally, you can have fewer nodes. For example, let's say some node is outside here, some node is outside here. So 3 and almost half node, okay? But at the same time, if you want to put a bunch of these vertically, not only 4, but the 5th one will sit there, for example. So also, if you want to have more than one slot, you have a bunch of room to put them. So personally, I like vertical designs more. And the next episode, I will start designing a vertical graph design. It will be involved. I will make a graph, but for simplicity, I will evaluate in loop. I don't care about checking its children. Okay? This is the first iteration of our video series. In second iteration, I will, it won't check its children. In second iteration, I will check its children. In third iteration, we will add the start and end nodes, and we will check if only one node needs to be evaluated. So we add that feature. After that, we will branch off and design our real node graphs. One behavior tree, so that's another totally video series for you. One quest and dialogue series. And one very simple math series. I think I will forget about this guy. It's junk. So 2 branches, one for behavior trees, one for quest and dialogue. And again, it will be quest and dialogues. So as you can say, a node graph video series will be a lot more episodes than something like an item system. Also, one more thing. I want to come back. Come on, why are you sticking there? I want to come back to my item system now that I called it in future. I have something to do with item system. One, I don't like deleting the scripts. I will remove it. Instead, I will put them inside the backup folder. 2, I will try to use reflection plus custom attributes to write those item categories scripts more wisely. So we will put an attribute on each interface that we want. Then we will design our graph, or not graph, design our editor at runtime. You remember we had some checkboxes for different interfaces. We will design it by reflection and reading these guys. And at the end, when we have this, we will use reflection again, read properties, and put them in a script. It won't eliminate the need to write code, but it makes your job much easier. But it's for much later future, because I want to start my node graph. I'm still doing R&D on this. That's why I said it's on hiatus. So we will start our node graph system. As I said, first iteration is a node graph that evaluates every node in a loop. And believe me, by itself, it's interesting, and I'm sure you will enjoy it. So have fun, everyone. Bye-bye.